So, dear students, today we will, sorry, maybe it will be better without this mask. So, once more, dear students, today we will start a new topic, and the topic is called random processes, which is connected to the previous topics of probability and also statistics, but it will be new in the sense that we will add a temporal item. So, the definition of a random process is such that it is a family or a system of random variables with some index small t, and this index small t denotes the time. So, some examples. Here we have time, let's say in years. And on the vertical x, we will have classes of car. Insurance, which is something what you had in your second homework. So, the insurance work in the following way. When a client comes to the insurance company and he or she wants to have car insurance, he or she will start in the first class and will pay the basic price for the insurance. Then, if the client drives without an accident, he will jump to the second class, where is some discount of the insurance price. If for the whole year the client drives without an accident, he will jump up, but it can happen that the client had some accident during the year and he wanted the insurance company to pay him some money and so on, so he becomes more expensive for the company and he or she will fall down to the first class again. And then he or she will drive without an accident, so he or she will jump up. Then the client jump to the third class, and if he or she won't have accident for next years, he will stay in the third class, and it can happen that in the 6th or 7th year there will be again some accident, so he or she will jump, and so on. And so this is the example of a random process where the client jumps or fall down from one class to another class. Or another example. Again, we consider time. And on the vertical x, we will have exchange rate of, let's say, euro with respect to Czech crowns. And the time will be measured in days. So the exchange rate, which will be plotted here, is the exchange rate which you can read in the newspaper every morning. So let's say that everything will be somewhere around 27.50. And the exchange rate is changing from day to day. Or it is not necessary a family of some points in random heights. It can happen that we consider the time to be continuous. So we can consider the time, let's say, again in days, and on the vertical x, we will have the number of car accidents till the time t. And then the plot will be continuous. The car accident, let's say, reported to the insurance company, which follows this number of accidents. And so let's say that for the whole day there is no accident, and somewhere in the middle of the second day there will be one accident. Then again for half a day or some part of day nothing happens, and somewhere in the middle of the third day there will be an accident. Then there will be almost 2 days without accident, and in fact the number of accidents can be observed in arbitrary time in continuous sense. And so we can ask, what is the number of accidents till the beginning of the 6th day? And we can see that it is 1, 2, 3, 4 accidents. And so we can ask in arbitrary continuous time about the number of accidents till that time. Or again, we consider the time, now let's say in hours, and we observe the temperature. And so, for example, today I think that the temperature is somewhere between 5 and 10 degrees. So maybe it was a little bit colder around the midnight. Oh, it was quite fast. So let's say this is the evolution of the temperature today. And all these plots are plots of realizations of random processes. The differences between these plots are in the discrete and continuous values which we take, and in discrete and continuous time we consider. And this is the first division of random processes. So when we consider the index set T to be continuous, so it is the case of these two plots below, we talk about continuous time. In the upper plots, we talk about discrete time. And the second division is with respect to the taken values. So in the left plots, the values which we take are discrete, and they are the numbers. Here is the order of classes, here are the numbers of accidents. So when we consider the discrete set of values which can be taken, we talk about discrete states. And in these right plots, we considered some continuous values, continuous things. So in these cases, we talk about continuous states. So in fact, we consider 4 types of random processes. The random processes with discrete states and continuous states respectively, and the random processes with discrete time and continuous time respectively. Today, we focus on the first case when both the time and the states will be discrete, and we will assume a special property of such processes called Markov property. And before I start with this topic, I just tell you about few properties of random processes in general, and then we will focus on these Markov processes. So the property I want to talk about, because it will be considered also in the topic of Markov processes, is the stationarity of random processes. And we consider 2 types of stationarity. The first one is weak stationarity, and the second one is strict stationarity. And I won't explain the definition. I will mention the definition next week when we have more time for this. But I just explain the difference. The weak stationarity is connected to so-called autocovariance of the process, and the autocovariance is defined here in the 4th line of the definition as the covariance between 2 values whose distance is constant. And the process is called weakly stationary if this autocovariance function is constant. What does it mean? It means that the correlation, so it means the rate of dependence between 2 values in 2 times which are between which the distance is the same, is constant. So it means that the process doesn't change the dependence, but it allows to the process to have some drift, to have some trend. And so it can happen that the process is increasing, but it cannot happen that the dependence between, let's say, the time 3 and 5 is different from the dependence between the time 10 and 12. So when the distance between two times is equal, then the covariance, the rate of dependence between the values of the processes of the process is the same. While the strict stationarity requires the same, but it also requires the process to be in the same level. So it doesn't allow the process to grow, to decrease, to have some trend. So this process is not strictly stationary, it is only weakly stationary, because the probability that in the time 5, the value is below, some level A, is higher than in the times 10, 11, 12. So it's difficult to describe something without telling the strict definition. But the difference is such that the weak stationarity requires only the stationary dependence, while the strict stationarity requires the process to lie in one level, approximately. I will talk about this next week. So now let's skip the stationarity, and when I will talk about stationarity in our topic of Markov processes, I will recall what exactly I mean. So let's go to the topic I promised you from the beginning, and it is the topic of Markov chains with discrete time. So as I said, Markov chains with discrete time are random processes with discrete time. Of course, it is in the title. But when we talk about chains, it means that we talk also about discrete states. And because we have, in fact, the chains of values. And these processes with discrete states and discrete time must have Markov property, which is defined in the definition below. The probability that in the time n+1, the process is in the state J, conditionally on being in the state I in the previous time, and being in the state I n -1 in the previous time, and so on, is equal to the probability that in the time n+1, the process lies in the state J, conditionally on being in the state I in the time n. How can we imagine this situation? Imagine it so that n is the time now. So now, the process, the evolution of some random values, are in the state in the value I. And the probability that in the next step, the process will be in the state J is independent on the previous evolution. And because the probability that the process will be in the state J when now it is in the state I, and in the previous times it was in some different states, is equal only to the probability that now we are in the state I, and everything what was before is forgotten. So that's the Markov property. The future evolution of the values depends only on the present value, on the last known value. So the Markov property from the definition means the future evolution of the values depends only on the last known value, but not on the evolution before. That's how we can describe the Markov property by words. So, some example of Markov chains. The simplest example which you can have is the example of random walk. The random walk is described briefly on the slide, and in fact the random walk means that is it denoted as x? Yeah, it is. That we start in the value 0, and with probability 1/2, we will jump to the value 1. With probability 1/2, we will fall down to the value -1. So let's say we will jump to the value 1. And again, with probability 1, we jump up to the value 2 with probability 1/2. With probability 1/2, we will fall down to 0. So let's say that we jump up. In the next step, with probability 1/2, we jump, and with probability 1/2, we will fall down, and we will continue in this way in the whole evolution of the process. So always when we are in some value, we can either jump or fall down for 1 unit, and we don't care about the previous evolution. And that's the Markov property. Of course, in practice, we will consider more sophisticated processes than this one, but this is really the basic example for your imagination what this Markov property means. Before we start with some example, which will follow us for the whole lecture today, we will mention a few terms. So, since everything depends only on the value I in the present time and the value j in the future time, in the time n+1, we will denote these probabilities that we will get from the value I now to the value j in the next time as Pij. In the brackets we can write n+1, but usually we suppose, and this is the definition below, that these probabilities, which are called transit probabilities, don't depend on the value n, on the time n where we are, but it depends only on the difference of the time. So it means that in the first case, we care about the transit probabilities from I to j in one step. And so for example, the probability of getting from I to j from the time 2 till the time 3, or from the time 5 till the time 6, from the time 20 till the time 21, and so on and so on. And so when we consider when we care only about the difference of the times and not on the time where we are, we call this process homogeneous. And in this lecture, we will consider only these homogeneous processes. It doesn't depend on the time n where we are, but as I said, it depends on the difference of times. Because it's not necessary to calculate only the probability that in the next step we will be in the value j. We can be interested also in, let's say, in the value, in the probability of values j in 2 steps or 3 steps or more steps. So when we are interested in the probability that we will get from the value I now to the value j in m steps, then we call it the transit probabilities from the state I to the state j of the probabilities of the mth order. Yeah? And again, we suppose that the probabilities doesn't depend on where we are in the chain. It depends only on the difference, on the number of steps between these 2 values. Yeah. So it must be satisfied. Oh, I will show you in the example everything what is written here. So what I want to tell you, the last definition is the definition of metrics of the transit probabilities, because that's something what you should construct in your second homework. And the matrix of transit probabilities is the matrix consisting of these Pij when we suppose that the process is inhomogeneous. Because when we suppose, I go back to the previous slide, when we suppose that these probabilities to get from the value I to the value j in 1 step don't depend on the value n, we are interested only in this Pij. So we have only this Pij, the probabilities of getting from I to j in 1 step. And these probabilities can be ordered, can be put to the matrix, which is called the matrix of transit probabilities. It will be easier to show you some example. And the example is the following. We will care about whether in a town on Adriatic coast, the town which I mean is called Baška Voda in Croatia, and it is a very sunny place, especially during the summer. Period. We will consider 3 types of days. S as sunny day, R as rainy day, and C as the cloudy day. So our process will have 3 states. The states won't be given by numbers, it will be given by letters, but so what? So we will consider these 3 days, which are the states of the random process xn, and n is from 0 to some large n, but in fact, from theoretical point of view, we should consider infinity in order to make it mathematically correct. Yeah, but of course, when I said that we will consider the weather in summer period, there must be some finite number of days. Not important for what I want to show you. So the process describes the weather on the nth day of the summer season. And we know the weather behavior is the following. If there is raining in some day, with probability 0.7, it will be sunny in the next day. So in fact, this 0.7 is the probability that if there is a rainy day today, it will be sunny tomorrow. So the probability when there will be sunny tomorrow, when today it is raining. And if there is cloudy day with probability 0.6, it will be sunny the next day. And if there is a sunny day with probability 0.8, it will be sunny tomorrow. If there is a sunny day with probability 0.1, it will be rainy tomorrow. And with probability 0.1, it will be cloudy tomorrow. And now if there is rainy, it will be rainy tomorrow with probability 0.2. So it means that with probability 0.1, it will be cloudy if it is rainy today. And if there is cloudy, it will be cloudy tomorrow with probability 0.1. And with probability 0.3, it will be rainy tomorrow. And I don't know whether it is good seen or not in this graph what happens. So from my point of view, it is better to see it in a matrix of transit probabilities. So the matrix of transit probabilities is the matrix with elements Pij, where Pij is the probability, I recall, probability that in the following time we will be in the state J when now we are in the state I. So what does it mean? Our states are sunny, rainy, cloudy, sunny, rainy, cloudy, and now we will fill the probabilities from this plot. And this element means the probability that if it is sunny day today, it will be a sunny day tomorrow. The probability is 0.1. 0.8. Here, we put the probability that it will be rainy tomorrow if it is sunny today. The probability is 0.1. And the probability that it will be cloudy tomorrow when it is sunny today is 0.1 again. And so we will fill the table in the sense and we obtain what we wanted, the matrix of transit probabilities. And so, for example, this number 0.3 is the probability that it will be rainy tomorrow when it is cloudy today, and so on and so on. And this matrix of transit probabilities has many practical usage. First, before I will show you the first usage, I will mention a special property of this matrix, and the property is that the sum of the numbers in each row must be equal to 1. Why? Because imagine the situation. Today it is a sunny day, and tomorrow it must happen that the day will be either sunny or rainy or cloudy. Some of these three situations must happen. So the probability that it will be either sunny or rainy or cloudy together must be equal to 1. And so always when you construct this matrix of transit probabilities, the sum in all the rows must be equal to 1 because the process must go to some of these states. So be careful when you construct this matrix and always check whether the sum in the rows is equal to 1. Okay, and now the practical usage of this matrix. So, because we suppose that the probability of the future state depends only on the present state and not on the previous evolution, we can apply the chain rule from the probability theory to these processes, but it will be much simpler. The chain rule from probability theory. It was, I think, the second lecture. Give us the description how to calculate the probability of the intersection of n random events. And it says that it is the probability of the first event times the probability of the second event conditionally on the first event times the probability of the third event conditionally on the intersection of all previous events and so on times the probability of the last event conditionally on the intersection of all previous events. And that's exactly the same what we are doing here, because I told you that time that it is in fact the evolution of some processes, of some actions which go step by step. But now these intersections are not important because we know that everything, not this one, and these ones, they are not important because we know that everything depends on the last known value and not on the previous evolution. So in fact, in our case, this theorem says that when we care about the probability of some concrete evolution, so about the probability that in the time 0, we are in the value I0, in the time 1, we are in the value I1 and so on till the time n, when we should take the value In, is equal only to the probability that we start from the value I0, and then we use only the transit probabilities, because all these probabilities from the chain rule are in fact only the transit probabilities. So, for example, when we care about the evolution, that the first day it will be sunny, the second day it will be rainy, and the third day it will be cloudy, we calculate only the first day it will be sunny, the second day it will be rainy, the third day it will be cloudy, when we know that now when we come to the holiday it is sunny. It is nothing than the probability that it is sunny now, but it is equal to one because we know that now it is sunny, times the probability that we get from the sunny day today to the sunny day tomorrow, times the probability that from the sunny day tomorrow we will go to the rainy day the day after, times the probability that from the rainy day we will go to the cloudy day. And that's it. So nothing else, just this chain of transit probabilities gives us the probability of the concrete evolution of the weather. So it was the first usage, but it is not as interesting as the other two usage I want to show you. So the second usage I want to show you is how to derive the probabilities of the transit probabilities of the nth order from these probabilities. Imagine the plot. Here we have the time n, and here we have the three types of weather. And we care about the changes, about the transit probabilities in two steps. So about the probability that we will go, let's say, from cloudy weather to the rainy weather, but in two steps. Not in one step, it is given by the matrix, but we care about the transit probability in 2 days, in 2 steps. So, what can happen? It can happen that it is cloudy today, it will be cloudy tomorrow, and then it will be rainy in the third day. Or it can happen that when it is cloudy today, it will be rainy tomorrow and also the day after. Or it can happen that it is cloudy today, it will be sunny tomorrow, and then from sunny day we will fall down to the rainy day. So in fact, we considered 3 situations. What can happen in the day between? And all these 3 evolutions give us the situation that when it is cloudy today, it will be rainy in 2 days. So the probability that we will get from the cloudy day to the rainy day, the probability that we will get from cloudy day today to rainy day in 2 days is the probability that we go from cloudy day to cloudy day times the probability that we will go from cloudy day to rainy day. It is the probability of the way here below, plus the probability that from cloudy day we will go to the rainy day times the probability that we will stay in the rainy day. It is the probability of the middle way, plus the probability that from cloudy day we will get to the sunny day, and from sunny day we will go to the rainy day. And what this means, it is in fact the sum of the probabilities that from cloudy day we went to some other day k times the probability of k kr, the sum over all k from the set of our weather. So in fact, it is the sum over all states. And now I just recall one thing. When we calculate the product of two matrices, A and B, it is a matrix C, which is a matrix consisting of the elements Cij. And if we denote the elements of A as Aij and the elements of B as Bij, the elements Cij are given by the sum over all k from 1 to n of the product A ik times B kj. So, what does it mean? It means that this product is nothing than the product which gives us the elements of the product of two matrices. And in our case, our matrices are the matrix P and the matrix P. So, in fact, these transit probabilities of the second order can be also ordered to the matrix. The matrix is called the matrix of transit probabilities of the second order P2, and we derived that it is nothing than the product of the matrix P with itself. So in our case, when we want to construct the matrix of transit probabilities, it is the product of this matrix with this matrix, and we obtain the following. So in the first row and the first column, we have 0.8 times 0.8 is 0.64 plus 0.07 plus 0.06. So it is 0.77. In the second row and the first column, we have 0.56 plus 0.14 plus 0.6, so it is 0.76, and it will be 0.75 in the third row, 0.13, 0.12, and 0.11 are the probabilities in the second column, and 0.1, 0.1, 0.1 are the probabilities in the third column. And each number in this matrix gives us the probability of getting from the weather corresponding to the row to the weather corresponding to the column in 2 steps, in 2 days. So for example, this 0.12 is the probability that if it is rainy today, it will be rainy in 2 days, and so on. And now, look to the matrices. You can see that the probabilities that we will get to some concrete days are much closer than at the beginning. Here the probabilities that it will be sunny in 2 days are very close to each other independently on the weather today. And when we continue to multiply these matrices, we will notice that the probabilities are closer and closer. And finally, in the infinity, we will obtain only one number in each column. And this number is called, or these numbers, vector of these numbers, is called the stationary distribution. And it is the third usage of this matrix of transit probabilities. So, before I start to show you how to find this stationary distribution, I just mentioned that the relationship that the probability of the second order is obtained as the second power of the matrix can be generalized to the relation that the probability, that the matrix of transit probabilities of m plus nth order can be written as the product of the matrices of transit probabilities of the mth and nth order, respectively. But it is natural because it is not important whether we consider only one step here and one step here, or m steps here and n steps here. And so the idea is the same. It must be always the sum over all states in some time in the middle of the considered interval. So I will skip this and let's go to the stationary distribution. So, as you can hear from the title, stationary distribution, it is connected to the stationarity of the random processes. And I told you that we are going to some number which gives us the probability that in n steps, when n is large enough, we will be in a sunny or rainy or cloudy day, respectively, independently on the starting day. And what does it mean? It means, in fact, when it is independent on the starting day, that it is the probability that when we choose randomly the day from the season, it will be sunny or rainy or cloudy, respectively. So it means that from economical point of view, we can calculate that during the season, there will be approximately such a ratio of sunny days, such a ratio of rainy days, such a ratio of cloudy days, and we can, for example, have some some given number of umbrellas, some given number of cocktails for sunny days, and so on and so on. And so from economical point of view, we can calculate with such a ratio of the corresponding days. How we will find the stationary distribution? Of course, we won't multiply these matrices of transit probabilities to the infinity. It would take quite a long time. So we will construct we will construct a system of equations, of n equations, which we will solve. We will denote the ratios of the concrete days as pi. So it will be pi s, the ratio of, the ratio is not a good word now. I will write only today. And tomorrow. So let's say that for today, the probabilities of sunny, rainy, and cloudy days are denoted as pi s, pi r, and pi c. And these probabilities that today it is sunny or rainy or cloudy, respectively, must be equal to the probabilities tomorrow. We know that tomorrow the probability of a sunny day is equal to the probability of sunny day today times the probability that the day will stay sunny, plus the probability, so it means the ratio of rainy days, which becomes sunny tomorrow, and plus the probability that it is a cloudy day times the probability that such a cloudy day becomes sunny day. And it must be equal. The same happens in the second row. The probability that tomorrow it will be a rainy day is equal to the probability that it is a sunny day today times the probability that this sunny day becomes a rainy day, plus the probability that it is a rainy day and it will stay rainy, plus the probability that it is a cloudy day and we will go from this cloudy day to the rainy day. So in this way, we obtain the system of three equations where all these probabilities can be again obtained from the matrix of transit probabilities. So again, we use this matrix of transit probabilities to find the stationary distribution, and we don't have to calculate the product of infinite number of such matrices. We can solve only the system of equations. So in our case, it is the probability of sunny day which stays sunny is 0.8 plus the probability that the rainy day becomes a sunny day plus the probability that cloudy day becomes a sunny day. And when you look to the coefficients, it's nothing than the first column. So when you construct the system of equations, you always go in columns to put the coefficients to the equations. So now we consider the second column, which gives us the coefficients for the equations. see. And now we have 3 equations with 3 unknown variables, and we will solve the system. Okay, it would be nice. But there is a problem that the system of these 3 equations is not regular. So from this system of equations, we would get an infinite number of solutions. That's the problem, but this problem has an easy solution. We know that these 3 numbers are the probabilities of the concrete types of days. And we know that one of these types of days must occur. So we know that the sum of these equations of these values must be equal to 1. And that's the last thing, last equation which we need. So now we can consider only 2 of these equations, and we will solve the system of these 2 equations plus the last equation which I added. And how to use it in this case? For example, we can see that in the third equation, we have all 3 probabilities with the coefficient 0.1, and we now, from here, that this sum is equal to 1. And so we directly know that the probability of a cloudy day is equal to 0.1, which is not surprising, because we could see that from the beginning, in the third column, we have the probability 0.1. So the probability that it will be cloudy day, independently on what happened before, must be equal to 0.1. Okay, so we can put it, for example, to the second equation. So PR is equal to 0.1 S plus 0.2 pi R plus 0.3 times 0.1. And what can we do with this? It means that 0.8 pi R is equal to 0.1 pi S plus 0.03. So pi R is equal to 1/8 pi S plus 3/80. And now we have pi R. We can put it, for example, to the last equation. And in this way, solving this system of equation, we will get the result that ES is equal to 23/30. Pi R is equal to 4/30, so it means 2/15, and pi S is equal to 0.1, so it means 1/10. So just to be sure, when we rewrite everything to the form something over 30, we can see that really the sum of these three probabilities is equal to 1. So this is something what we can call the stationary distribution. And it means, from economical point of view, that we can calculate with these probabilities to be the probabilities of these three types of days. So it means the ratios of these types of days during the season. And that's the meaning of the stationary distribution, which can be formulated in the following theorem. And the theorem said that if the homogeneous Markov chains is stationary, meaning if the initial distribution, so it means the probability that the first day of the season is sunny, rainy, or cloudy. With these probabilities, then the Markov chain is stationary, and it holds that the probability that in arbitrary time it is in the state J is equal to pi J. So one more theorem considering the stationary distribution is the following. So concentrate on the point 2. So let's suppose that the stationary distribution exists. Then the pi j, the jth item of the distribution, is equal to the limit of the transit probabilities of the nth order, and the limit for n going to infinity. And for all these states, it holds that these probabilities are positive, while it is in fact to be equal to the probability that in arbitrary time we are in the jth state. That's something what I said. So it is only mathematical formulation of what we obtained. And if the states are periodic, okay, I will mention this later. So this was the usage of transit of the metrics of transit probabilities, and now in the last few minutes I will tell you something about the states classification, which is not so important topic for you, but you should know about this when we talk about random processes. So the classification of the states is based on the assumption that our process starts from the state from the value j. And then we denote let's keep the first point and let's go to the second point. Let's define the tau j, or sometimes denoted as tau j, and in the brackets we have the value 1. The time of the first return of the chain to the state j. Yeah? So the number 1 is useless for us because we will consider only the first return, but only in order to the notation correspond to the notation of the literature which you can find considering this topic. I will put 1 as the first return to the brackets. But it's not important. The important is the value tau j, which is the time of the first return of the chain to the state j. And mu j will be the expected value of this time. And so this time is random, of course. And this mu j denotes the expected value of this time, while it can happen that sometimes the time is periodic in the sense that it cannot happen that it will go to the same state in the following step. Let's go back to our random walk. The random walk started in the value 0, and with probability 1, it jumped to the value 1. With probability 1/2, it fall down to the value -1. But it couldn't happen, it cannot happen that it will stay in the value 0. It must go either up or down, but it cannot stay in the value 0. So let's say that it will go up, and then in the second step, it can fall down, or it can go up. So let's say that it will fall down. But it returned to the value 2 in 2 steps. Or it can happen that it will jump up, then fall down, and then fall down to 0. But again, it is the even number of steps between starting from 0 and return to 0. And so it can happen in the case of this random walk that only in the even times we can return to the value 0. Concerning the when we consider the value 1, there are only odd times in which we can be in the value 1. And in even times, we cannot get to the value 1. There's no way to get to the value 1. And so in this case, we talked about periodical states. It is the last definition of the following slide. And so in the case that there exists some number of steps, some difference between steps, which is larger than 1, where the process can return to the states, we talk about periodical states. And how can we divide the states otherwise? The basic division is to the states which are recurrent and to the states which are transient. The second case are the states where there exists a probability that the process won't come back to itself. It is, for example, in the situation that the transit probability, we consider only 2 states, and the matrix of transit probabilities are 0.5, 0.5, 0, and 1. It can happen that when we leave the state 1, we won't return to the state 1, because when we get from the state 1 to the state 2, we will stay in the state 2 forever. So there exists the probability that when we leave the first state, we won't return. And this is the case of the transient state. While in the case that the probability that we will get back to the state in a finite time is equal to 1, we call the state to be recurrent. And it can happen in some special situation that the state is recurrent, but the expected value of this time is equal to infinity. In this case, we call the state to be null recurrent, while in the normal situation that the expected value of the time, so it means the mean time for the process to return back to the state J is finite, we call the state non-null recurrent. It can happen only in some special situations when the probability, when the number of states is infinite. So we can discuss it on exercise. We have no time for it now. Yeah, but it can happen that even when the probability that we will go to the state, we will return to the state in finite time, surely with probability 1, the mean value, the mean time of return is equal to infinity. But let's skip this special situation and just talk about the connection of this of the state classification with the stationarity and with the limit probabilities. So let's consider the state which is transient. So it is the state where there exists a probability that the process won't return to this state again. Then, of course, if the probability that we won't return to the state is equal to 0, then when the probability that we won't go back is positive, then the limit of transit probabilities to this state must be equal to 0. And because if there exists a probability that we won't return, in infinite time, it must happen that the process won't return. It must happen sometimes that the process will leave somewhere to some state from which it cannot go back. So then the limit of the transit probabilities of the nth order, and the limit is for n going to infinity, is equal to 0, independently on the state I from which we start. And so it holds for all states I from which we start. The same situation is in the case when the time, when the state is null recurrent. Even when it is recurrent, the mean time of waiting for the return is equal to infinity. And it means that also in this case, the limit of transit probabilities of the nth order, the transit probabilities to this state is equal to 0. And because the mean time, the average of the times is equal to infinity. And in fact, it follows, everything follows or can be better seen from the part C of the theorem, which says that when the state is null recurrent, so it means the classical state, it was the state sunny, rainy, and cloudy in our example, where we can go from each state to each state. Then the limit probability is 1 over the mean time waiting for the return. And in fact, it makes sense because imagine the situation that we return to the state 1 in average in each 10th step. And so it means that in 10% of steps, we will go back to the state J. It means that I don't know, when you leave your parents, you will go back to your parents in average each 10 days. So then the probability that a randomly chosen day is the day when you visit the parents is 1 over 10. And it is the same situation here. When the mean time, when the period of returning, but I don't want to talk about period because it is another time. When the mean value, the mean time, the average time of returning to the process is mu j, then of course the probability that we are in infinite number of steps in this state j is equal to 1 over mu j. And now you can see the property B I was talking before. If the mu j, the average time, is equal to infinity, then this probability is equal to 1 over infinity, and it must be 0. So you can imagine the property B in this sense. And when we consider the periodical state, then we must consider the limit of transit probabilities from j to j, but only in n times the period of this state steps. Otherwise, it has no meaning. Otherwise, we know that this probability is equal to 0. And so we must consider this probability, each n times the jth step. And in this case, of course, the probability must be dj times mu j, because we considered only each djth step. And so it is the connection of this state classification and the transit probabilities. So I don't want you to calculate or to classify the states of some Markov chains, but I want you to understand that when we know the classification, when we know the properties of the state, it is easier for us to derive the transit probabilities and to derive the behavior of the Markov chain. Okay, so that's all I wanted to show you today, and thank you for your attention.